Welcome folks, a video today talking about advanced techniques of integration. Here we're talking about the strategy of partial fraction decomposition. I'll go ahead and give you an overview and then we'll talk about partial fraction decompositions as they're divided up into two different categories, one in which our rational function has linear factors and another in which it has irreducible quadratic factors. So again, here today we're talking about integrals of rational functions. So I'll remind you that a function is a rational function if it can be written as f of x equals p of x over q of x, where p and q are both polynomials. So just a reminder, a polynomial is a function that has non-negative integer powers of x. So as it turns out, we know about some integrals of rational functions. Here are a few simple ones. For instance, this first one we know integrates just like a natural log. The second one integrates quickly too. You might recognize the function in the integrand as a derivative of the arctangent function. As it turns out, all of these rational functions come up in our indefinite integrals, and we'll need to be able to evaluate those quickly. Here's an example that sort of shows us what's at the core of integrals of rational functions. Given these two simple rational functions, 2 over x plus 1 plus 3 over x minus 1, we know how to find a common denominator and put these together into a single rational function. So here's a perfectly good rational function that results from, again, just finding common denominators and simplifying. 2 over x plus 1 plus 3 over x minus 1 can be written as 5x plus 1 divided by x squared minus 1. Now in terms of integrals, that gives us something interesting. Since the two integrands are equal, we know that the antiderivative of those integrands is also equal. So the point of partial fraction decomposition is going backward in this process of finding a common denominator and putting things together to decompose a rational function into factors that we can integrate quickly. So that's the goal for today, is to see several strategies to do that. Before we do that, though, we'll talk about polynomial long division. So polynomial long division is a strategy that you've probably seen before. We'll go ahead and use polynomial long division to simplify this rational function. So here's what polynomial long division tells us about this rational function, x cubed over x minus 1. We can first divide x into x cubed, getting x squared, subtracting the resulting product, and similarly with x and 1, so that x cubed over x minus 1 can be written as x squared plus x plus 1 plus 1 over x minus 1. Now, of course, if those two functions are equal, their integrals should be equal too. So again, here is what our polynomial long division gives us. And since the two functions are equal, their integrals are equal also, giving us the general antiderivative for x cubed over x minus 1 as 1/3 x cubed plus 1/2 x squared plus x plus the natural log of the absolute value of x minus 1 plus an arbitrary constant. Now, as it turns out, polynomial long division is a strategy that you have to use in some cases. Whenever the degree of the numerator is greater than or equal to the degree of the denominator, we must first use polynomial long division to simplify our rational function. That turns out again to be a useful strategy. It doesn't always come up, and in fact, in the examples we'll see from here on out, we'll see that the degree of the numerator is strictly less than the degree of the denominator. And again, degree describing the highest power of x in the numerator and denominator. Okay, so let's go ahead and talk about some examples where we have linear factors in the denominator. When the denominator of the rational function p over q has simple linear factors, the bottom line is that the decomposition has one term per factor. So let's just go ahead and see some examples of, an example of these simple linear factors. So here's a perfectly good partial fraction decomposition for the integral of 5x plus 1 divided by x plus 1 times x minus 1. In this case, we see the denominator has two simple linear factors. So again, the partial fraction decomposition will have one term per factor. Here's what that decomposition looks like. The decomposition in this case has form 5x plus 1 over x minus 1x plus 1 equals some constant a over x plus 1 plus some constant b over x minus 1. Now, some of you may have seen these decompositions before, perhaps in pre-calculus or something. There are a lot of different ways to figure out what a and b are. All of them involve what's called clearing the denominator. So let's start with clearing the denominator. So here's what we get when we clear the denominator, multiply left and right hand sides by x minus 1 times x plus 1. We find that 5x plus 1 on the left hand side is equal to some constant a times x minus 1 plus some constant b times x plus 1. Now, one thing you can do is expand this all out and equate coefficients, and we'll see how to do that a little bit later. Another thing you can do here is choose x strategically. So for instance, one strategic choice for x is x equal to 1. If x approaches 1, we see that the left-hand side becomes 6, the right-hand side becomes a times 0 plus b times 2, and we can quickly solve for b as 3. A second strategic choice for x is x going to minus 1. As x approaches minus 1, we see that the left-hand side is negative 4, the right-hand side is a times negative 2 plus b times 0. That gives us b equals 2. So here's our partial fraction decomposition. Our partial fraction decomposition is that 5x plus 1 over x plus 1 times x minus 1 is 2 over x plus 1 plus 3 over x minus 1. Now, you may recognize this example from our motivating example. We have gone the other way, taking this rational function apart. But if you wanted to check, you could check just by putting it back together. Now that we have the partial fraction decomposition, evaluating the integral is as quick as evaluating two integrals that end up involving natural logs. So again, here's that partial fraction decomposition. Integral of one rational function is integral of the decomposed rational function. The decomposed rational function is quick to integrate up, again, as we saw before, to natural log of x plus 1 in absolute value plus 3 times the natural log of x minus 1 in absolute value plus a constant. Simple linear factors, one term per factor. Let's go ahead and look at repeated linear factors. In the case where the denominator has repeated linear factors, the decomposition has one term per factor, including repeats. So how do we know if a denominator has repeated linear factors? Those can be factored as something like x minus a to the k power. Okay, so again, when you have a quantity x minus a to the k power for some k greater than or equal to 2, this is what we mean by a repeated linear factor. So let's see an example involving repeated linear factors. Here's a perfectly good rational function, the integral of 10 divided by x cubed minus 5x squared. So let's go ahead and factor the denominator, and we'll see what the decomposition looks like. So here's our decomposition in this case. We see that 10 over the quantity x cubed minus 5x squared can be factored as 10 over the quantity x squared times x minus 5. Of course, this x squared is our repeated linear factor. So one term per factor, including repeats. And then, of course, we have our simple linear factor with term c over x minus 5. Again, the first thing we'll do here is clear the denominator and then make a couple strategic choices of x that make our life easier. So we can see after clearing the denominator that 10 is equal to a times the quantity x minus 5 plus b times x times the quantity x minus 5 plus c times x squared. So certainly two strategic choices for x are x equals 0 and x equals 5. When x approaches 0, a quickly simplifies as minus 2. When x approaches 5, c quickly simplifies as 2/5. And now it turns out we just have to choose anything else for x to figure out what b is. Okay, I ran a little bit out of space here, so I computed 10 is a times minus 4 plus b times minus 4 plus c when x goes to 1. This gives us that minus 4b is equal to 8/5. And if minus 4b is 8/5, it turns out that b is negative 2/5. So here's the partial fraction decomposition in all of its glory. We see our factor of minus 2 for a, minus 2/5 for b, and positive 2/5 for c. Once we had the partial fraction decomposition, the indefinite integral is quick to evaluate. So again, here's that partial fraction decomposition. And x to the minus 2 power is just a power function, integrates quickly. Of course, 1 over x and 1 over x minus 5 integrate like natural logs, and we're left with 2 over x minus 2/5 times the natural log of x plus 2/5 natural log of the absolute value of x minus 5 plus an arbitrary constant. Okay, so again, any repeated linear factor, the decomposition has one term per factor, including repeats. Let's go ahead and talk about irreducible quadratic factors. Irreducible quadratic factors are terms that don't factor over the real numbers. Oftentimes, these terms have form of something like x squared plus a squared. So again, any term that doesn't factor over the real numbers is an irreducible quadratic factor. And whenever we have an irreducible quadratic factor, the numerator of the partial fraction decomposition corresponding to that irreducible quadratic factor has a first order polynomial. Okay, so let's see an example involving that. Let's find an antiderivative of 2x squared minus x plus 4 divided by the quantity x cubed plus x. We'll start by factoring the integrand and then writing down its partial fraction decomposition. So here is the factored form of the integrand, 2x squared minus x plus 4 divided by x times the quantity x squared plus 1. Of course, corresponding to our simple linear factor is a term of the form a over x, and corresponding to our irreducible quadratic factor is a term of the form bx plus c over x squared plus 1. Again, we can clear the denominator multiplying through by the denominator on the left-hand side. Now, as it turns out, we can still find the constant corresponding to that simple linear factor with a quick choice of x. When x is 0, the bx plus c term is zeroed out, and we can see that a has to be 4. Now, to find the other constants, the b and the c, it turns out to be easiest to multiply out and match powers. Here's what I mean by that. So on the right-hand side, I've just multiplied out a times the quantity x squared plus 1 and bx plus c times x. Now I've regrouped in descending order of the polynomial to write it as a plus b times x squared plus c times x plus a. The idea here is that the coefficient of the x squared term should equal, the coefficient of the x term should equal, and also the constant coefficients should equal. Here's what I mean by that. What I mean by that is that we should have a equal to 4. We already know that, but that's reassuring. We should have c equal to minus 1. And then we should have a plus b equal to 2. Since we already know that a is 4, that means b has to be 2. Excuse me, b has to be minus 2. Since we know that a is 4, b has to be minus 2. So here are those constants. A equals 4, b equals -2, and c equals -1. We can go ahead and write out the partial fraction decomposition now in all of its glory here. We see that a is equal to 4, and I factored out a minus sign from both of these terms so that we have b equal to -2 and c equal to 1. I'm going to go ahead and take this partial fraction decomposition apart just a little bit further to express it the following way, as 3 individual terms instead of just 2 separate terms. So again, here is one more separation where I've gone ahead and taken this rational term and spread the denominator over both terms in the numerator. We can now see that the first part looks like a natural log. The second part does too, with a u substitution of x squared plus 1, and the third part just looks like an arctangent. So here's that indefinite integral in all of its glory. 4 times natural log of the absolute value of x minus the natural log of x squared plus 1 plus the arctangent of x. Oh, and that should be a minus sign, excuse me, let me fix that. So again, 4 natural log absolute value of x minus the natural log of x squared plus 1 minus the arctangent of x plus an arbitrary constant. Okay, great. Finally, one thing that might happen is you might have repeated irreducible quadratic factors. You may not be surprised to use our intuition from repeated linear factors. The decomposition will have one term per repeat with the linear numerator. Here's an example that illustrates that. This is not an example that illustrates that. Let me fix that. Here's an example that illustrates that. Let's identify the form of the partial fraction decomposition for the function f of x equals 1 over the quantity x times the quantity x squared plus 4 all squared. So we can see this term of the form x squared plus 4 all squared is a repeated irreducible quadratic factor. So again, corresponding to our linear simple term in the denominator, there'll be one factor, and then one per repeat for the irreducible quadratic repeated. So this is the form of the partial fraction decomposition. 1 over x times x squared plus 4 all squared has form a over x plus bx plus c divided by x squared plus 4 all squared plus dx plus e over x squared plus 4. So again, the one term corresponding to our simple factor and the two separate terms per repeat with a linear or first order polynomial in the numerator. As you can imagine, this gets really, really messy, really, really fast. I won't ever ask you to do this, but you should know that this is what that decomposition looks like. Okay, one last comment here. It turns out that not all rational functions require a partial fraction decomposition. Here's an example of one that doesn't. In order to see why it doesn't, let's have a look at the denominator here and rewrite it a little bit by multiplying out the denominator. Now, one could use a partial fraction decomposition on this. However, if you notice that x cubed plus 3x has a derivative that looks like 3x squared plus 3, there's a u substitution that's suggested by that observation. That u substitution is u equals x cubed plus 3x. When u is x cubed plus 3x, the derivative du is 3x squared plus 3, which is exactly 3 times the numerator. Substituting and simplifying, we see that in u world, the integrand becomes 1/3 1 over u du, which quickly integrates as 1/3 natural log of u. Back in x world, of course, that's exactly 1/3 natural log of x cubed plus 3x plus an arbitrary constant. So here again is that indefinite integral, 1/3 natural log of the quantity x cubed plus 3x in absolute value plus a constant. You get the same thing if you tried a partial fraction decomposition here, but you would have gone to a lot of trouble without really needing it. So always try those substitution techniques first if you can. All right, folks, hope you have enjoyed this video on partial fraction decompositions. Have a great day, and we'll see you next time. Bye-bye.